Don't stop the physics tonight. Okay, so we're looking here at a electric field that's generated between two parallel plates connected to a battery, 45 volts, and we know the electric field is 1500 volts per meter. So first, let's just do this. Let's draw our parallel plates in. Let's give one side of the battery a 45 voltage, and the other side of the battery we refer to as the ground, 0 volts. Really, these might not be 45 and 0, they could be 90 and 45, but the difference needs to be 45 on them, and traditionally for a battery, the 0 volts is our ground there. We know that for a parallel plate scenario, if this is our quote-unquote positive side, and this is our negative side, the lower potential, we know our electric field is going to run high to low here, so the 45 to 0. These lines are equally spaced apart because they are a fully uniform electric field on the inside of this. And we know that whenever we get to the edges, we're going to get kind of a little edging effect here like that. So we got an edge effect just like that, which is causing that wrap. We know here that our electric field strength, E, is 1500 volts per meter, and our voltage is 45 volts. What we're looking for is how far apart are the plates. We're looking for some distance R. Now, we can only use this scenario because we have parallel plates here. If we had some sort of weird potential as a function of blah, 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 we couldn't really do this easily. It would take a little bit more understanding of how the electric field is being generated, some sort of formula to describe it. But because we know that this electric field is a constant between the parallel plates at any position in the parallel plates, here, 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 the electric field is the exact same, we can solve this. What we need to remember is that when we think about a voltage or a potential can be thought of as the field you are in and then how far you've moved along that field in a direction. And this is actually very similar to the idea of gravity. If we think about gravity, the field that we'd exist in is a gravitational field, and if we thought about gravity, this would be H, and this is our gravitational potential here, okay? If we wanted to make this a potential energy, we would multiply this by a mass, or we would multiply this by a charge, and we'd say QV equals work, which gives us energy, and M times the potential would give us the gravitational potential energy. But we're not looking for energies here. We're just saying, hey, look, I want to figure out this distance value here. And since I know the potential and I know my field is a constant, I can easily solve for R here and be done with all this. So all we have to say here is that the voltage divided by the electric field that we're given is equal to that distance, this distance between our two plates right here, which is R. That just gives us here that the voltage drop is 45, and that's volts divided by an electric field of 1500 volts per meter. And if we see that, our units work very nice for us here. The voltages divide out. The meter is in the denominator, which means it's going to flip up to the numerator, which is going to give us a correct answer, and we're going to get 0.03 meters for our final value. Okay? And like I said, this really only works when our electric field is a constant here. If our electric field is not a constant, we have to do much more complicated mathematics via calculus, and we need to know an actual function that describes our electric field. But in this case here, we can get away with this very, very straightforward equation. V equals ER for the electric potential equaling the field and the distance along that field as well. Okay? So nothing much to it. With that, this problem is finished. Take it easy. Adios.